This example illustrates the construction of a tie-back wall. There are a number of features here that we will illustrate. To begin with, we want to illustrate the excavation procedure, and we want to illustrate the use of structural elements, and in general the construction simulation sequence that's involved in a project like this. So the exercise is to establish the in-situ stress state, and then to install the sheet pile wall and excavate down 4 meters. Then once that's been done, then to simulate the installation and pre-stressing of the upper anchor, and we will simulate the anchor that as having a grouted length, which will be a beam, and a free length, which will be a bar. Once that has been done, we'll go to another analysis to excavate down another 3 meters, then install and pre-stress the lower anchor, and then excavate down the last 2 meters. In the essence of time here, we have provided the material properties. However, you will have to define the boundary conditions that simulate the excavation and removal of the material. In the end, we want to view and evaluate the forces and moments in the structural member. Going to GeoStudio then, and opening up file SIG06. There is one analysis in the file, and the geometry has been defined for the first analysis, the in-situ stress analysis. Inspecting the materials, key in materials. We have a homogeneous sand here. We're treating the sand as a total, defining the sand with total stress parameters, and for their illustrative purposes, just use a simple linear elastic model with a constant Young's modulus, a total unit weight of 20 kilonewtons per meter cubed, and a Poisson's ratio of 1/3, which represents a K0 of 1/2. The material has already been applied to the various regions. It's rather interesting to look at the mesh and how the mesher can mesh around the lines. It's very important to realize that these are geometric lines, and if we say draw mesh properties and click on a line, notice that we have said that we want to, number 1, generate a mesh along the line, and we want to have smaller elements along this line than the global average size of 1 meter. We have then meshed these 2 lines. They are 2 geometric lines in space. Going back to draw mesh properties, notice that we also have a line here, but the line has not a mesh. There is no mesh. This is unchecked. This is then for the purpose of connecting a bar between the grouted length and the wall itself. Turning off the mesh, the first step under the analysis is to do a in-situ analysis, and you should be getting used to doing the in-situ analysis now. Going to solve, we can solve for the in-situ stresses. Going to the results view, at this stage we need to know what is the lateral stress where the wall is going to exist. What is the stress distribution in the ground here before we come along and take away all of this material here? It is in essence a form of this stress that will have to be retained by the sheet pile wall and the anchor system. So the first thing now we need to do is to make a plot of the lateral horizontal or X stress where the beam, the sheet pile wall, will eventually be. Draw a graph. In-situ profile in the X direction. We are looking along this line here, and we see that our lateral horizontal stress is a linear line from the ground surface down to at the base of the problem where the total stress is 200 kPa. In a few moments here, we will apply a boundary condition to the edge of the excavation, which represents the removal of this stress. And in order to do that, it is a special type of boundary condition, which we will see in just a few moments. But before we go there, we notice that the rate of increase here, we have a total of 200 divided by 20 gives us 10 kilonewtons per meter. Or we can think of it as a fluid pressure of 10 kilonewtons per meter cubed. It's a rate of removing stress that is referenced to the top here. This is where we will reference the elevation here, and then the stress that is applied on the face of the excavation depends on the distance here, what we need to reference ourselves to the ground surface. So our first task then was to install the sheet pile wall and excavate down 4 meters. Going back to the define view, first of all, creating a new analysis, cloning the in-situ analysis. We say excavate 4 meters, say top 4 meters. And our parent is going to be the initial in-situ stress. And we are going to do a load deformation type of analysis. To keep the problem manageable for this illustrative case, we are not dealing with any pore water pressures, and that is why we use total stress parameters. However, we are going to get our initial stresses from the parent. Now we also need to install the sheet pile wall, and once again in finite element terminology we say that we wish the sheet pile wall into place. We do this by draw structural beam, and we have a sheet pile wall, and we have a Young's modulus, a cross-sectional area, and a moment of inertia, which represents the bending stiffness of the sheet pile wall. And we allow both tension and compression for the sheet pile wall. draw sheet pile wall, and we draw it on the lines or the edges of the regions. We need to now remove the top 4 meters, and so we want to remove the soil. We say draw materials, remove this upper 4 meters of soil so that it is not part of the finite element analysis. Then to begin with, we need to alter the boundary conditions. Say draw boundary conditions, fixing the left boundary in both the x and y directions. On the right, it is deemed to be the center of the excavation, so it's symmetric about the center of the excavation, and leaving it as a fixed x is adequate. Now we come to simulating the removal of the soil. And there was a stress here, and the stress plus the change in stress is equal to 0. So there was a stress, a compressive stress here. We want the stress to be 0. So in a finite element analysis, we have to apply a stress that is equal and opposite. So the stress was gamma times 4 meters. So gamma is 20 times 4 is equal to 4 meters is equal to 80 kilopascals. We now need to apply a pressure in the upward direction representing this 80 kPa. Under draw boundary conditions, the uplift 4 meter boundary condition has already been defined. However, the actual value of the uplift, for illustrative purposes here, we are going to use XY stresses, and we now have a positive 80 kPa acting on that surface, and we apply this to this line indicating the uplift representing the removal of the soil. Now the lateral force resulting from the removal of the soil, the boundary condition has been defined. Notice that we are now selecting here a boundary type under the stress category called hydrostatic pressure. We want to reference this hydrostatic pressure to the ground surface elevation of 20 meters, and the unit weight is minus, meaning pointing away from the face of the excavation, 10 kilonewtons per meter cubed. So we can now apply this pressure that pulls on the wall, so to speak. And to repeat, remember the stress was like this before the excavation was made. Now we have to remove that amount of stress represented under this triangle here. So we have installed the sheet pile wall and have simulated the excavation and the removal of the first meter of soil. And once again, we are doing a load deformation analysis. In this particular case, time is not meaningful, but nonetheless, we do use time to control the time stepping, And notice that we have a T here, and it is a T because the units for time are undefined. We simply say a duration of 1 and 1 step, and so we are going to do 1 increment of loading, and the loading is represented by the removal of the soil. Once again, clicking on verify, we should now be ready to analyze and solve this first step, and that is the removal of the upper 4 meters of soil. Briefly looking at the results view, turning off the mesh, looking at our deformed mesh, we see a slight amount of rebound at the base of the excavation. We can exaggerate it more by saying draw vectors and keep the magnification the same. In this particular case here, let's make this 2 for the time being, so we can see that everything is trending in the right direction. Going back to draw vectors, making the exaggeration or magnification back to 2. It'll become more meaningful when we have had more excavation in the construction process. Turning off the deformed mesh then, and going back to the defined view, we want to now install and pre-stress the upper anchor. Clone the excavation stage, install upper anchor. The parent now becomes excavate top 4 meters. Everything else is the same. We still have 1 time step or 1 load step. Installing the upper anchor, remember in our discussion on incremental formulations, we do not want to apply the excavation forces a second time. Therefore, we have to say draw boundary conditions, remove from a line this excavation force and this excavation force. But we now need to apply our anchor and pre-stress the anchor, draw structural beams, the upper anchor, and the upper anchor allows both tension and compression. Assign the upper anchor to a line. And now we need to assign the free length as a bar, draw structural bars, assigning it to the upper anchor, and we have a pre-stress of a minus 100. Minus 100 means that we are applying a tension to the bar. So we have installed our upper anchor and pre-stressed the anchor. We should be ready to solve this second analysis. Going back then to the key in analyses, we'll clone the simulation of the installing of the upper anchor by clone, and this time we want to excavate 3 meters, and the parent now comes the install upper anchor. We say draw materials, remove the material, And now we have to apply our boundary conditions that represent the removal of the materials. Draw a boundary condition. We have our lateral load, which is the same as before, and this time the lateral load is applied to the wall face that was just exposed, and we have uplift of 3 meters. Key in, we have an uplift of 3 meters, so 3 times 20, 3 meters times 20 kilonewtons per meter cubed is 60, and so we will have to enter here a value of 60. Applying it to the excavation face. And so now we are ready to analyze the removal of the second lift, creating solve. Going back to key in analyses, we now want to install the lower anchor. Once again, clone the most recent one, install lower anchor. The parent now comes the excavate 3 meters analysis. And now, once again, we don't want to apply the excavation forces a second time, so we say draw boundary conditions, remove these excavation forces, draw structural beams, the lower anchor, draw structural beams, selecting the lower anchor, bond length. Secondly, draw structural bars, the free length of the lower anchor. Once again, it has a pre-stress of 100 kilonewtons. Having installed and pre-stressed the lower anchor, we can now click on solve and solve for this phase of the construction sequence. Finally, we go back to define key in analysis, clone the analysis one more time, excavate 2 meters, and the parent becomes the lower anchor analysis. Removing the material, draw materials, remove, and now we have to apply the boundary conditions that represent the removal of the stresses. Draw boundary conditions. 2 meters of uplift. In this case, 2 meters times 20 is 40 kPa. And once again, we have to apply the lateral load representing the removal on the sheet pile wall. Recall that to repeat once again, and before we made any excavation, we had a stress distribution like that. So in this case, we are removing this amount of stress at this analysis stage. Solving then for the last analysis. Going to the results view, looking at the results by draw a graph. The wall deflection is probably the most interesting to start with. Notice that the wall deflection obviously is 0 at the in-situ stage. Holding down the control key, this is the wall deflection when the first 4 meters was excavated. This profile is all the way from the ground surface down to the bottom of the problem. So the base of the excavation was somewhere here at 4 meters. But what I want to draw your attention to is when we apply the second analysis, notice how the wall deflection has diminished by pre-stressing the upper anchor. The wall has moved back in due to the pre-stressing of the upper anchor. Then when we hold down the control key and make another excavation, then the wall moves way out again, deflects into the excavation, so to speak. And then when we pre-stress the lower anchor, the wall comes back ever so small amount, and then finally we make the last excavation and illustrating the deflection of the wall. And the deflection of the wall, of course, laterally is the largest toward the base of the excavation. This is a linear elastic analysis, and there's more to analyzing a tieback wall, but we have kept the example simple here to illustrate procedure and technique. The second point that is of interest is to look at anchor forces, and in this particular case we are looking at the force in the free length of the upper anchor. Notice that we had a pre-stress of 100 kilonewtons, minus meaning tension. Then when we excavated the middle 3 meters, the tension increased in the free length. But then when we installed the lower anchor, the tension decreased. In other words, tensioning the lower anchor slightly relaxed the force in the upper anchor, and then when we made the last excavation, a slight increase in the tension in the upper anchor. And what is rather interesting is that the maximum in the upper anchor does not occur at the end. It occurs after the middle excavation has been made. We can do the same thing with looking at the free length in the lower anchor, and in this particular case we had a pre-stress of 100 kPa, and by removing the last 2 meters, the force in the lower anchor increased to something like 555. We can also look at the moment distribution in the sheet pile wall. We can say set location, and once again the location is the sheet pile wall. And here is the moment distribution in the sheet pile wall when we install the upper anchor and then make a middle excavation. The moment increases very substantially due to the excavation of the middle 3 meters. Then the moment decreases a little bit due to the installation of the lower anchor. And then finally we have the excavation of the last lift. This just illustrates that sigma W can be used to look at things like moment distribution in structural members, and it is one of the big features about doing a soil structure interaction. We can also look at the axial forces in the grouted lengths of the anchor. In this particular case, we're looking at the grouted length in the upper anchor. And when we look at the case where we install the upper anchor, we are plotting versus the x distance. So we are going from the far end of the grouted length to the front end where the bar is connected. And here is the moment distribution in the grouted length. The moment distribution is not all that dramatic. It is very small actually. But more interesting is the axial force in the grouted length. And we notice that at the far end of the grouted length, the force in the bar is almost zero, increasing to some maximum at the front where the free length is hooked to the grouted length. It's interesting that the force in the grouted length is obviously not a constant, and this is one of the great benefits of doing a soil structure interaction, that we can look at variation in force in a grouted length, for example. Just looking at what happens to the axial force when we now make an excavation, a deeper excavation, and then installed the lower anchor, notice once again the axial force decreases, and then finally when we make the last excavation. We have a slight end effect here. This is because we have used the manner in which the axial forces are computed and the interaction with the other elements that are connected to the beam. We get a slight end effect here, but nonetheless it does show the general trend from small to big near the front of the anchor. This then illustrates how sigma W can be used to simulate the construction sequence of a facility like a tieback wall, where we have structural elements and beams and bars, and to illustrate how we remove the soil and how we apply boundary conditions that represent the soil removal. This is a rather simplistic example in some ways, but complicated in other ways. But nonetheless, the whole intent here has been to illustrate technique and procedure. That brings us to the end of this illustrative example and all the things that can be done with sigma W for a case like this. For those of you that are interested in deep excavations, we have a detailed case history that we ship with the software, and I would refer you to these case histories and go back to the detailed examples. There was a paper written that is described in the PDF document that goes with these examples, looking at 6 case histories in the Singapore area, and these were deep braced excavations in quite soft ground. So all of these simulations have been done with a fully coupled analysis where we consider both the stress changes and the pore water pressure changes, and we have compared these with actual measurements at these sites and compared it with another analysis done by a software called CRISP. Here we see one illustration where this is the measured, the green is the measured values of the wall deflection, the blue is the GeoStudio, and the red is the crisp solution. And very encouraging, the close agreement that existed between the two software products, and also the close agreement with the actual measurements, except perhaps near the ground surface. Nonetheless, anybody wishing to or interested in simulating braced or tieback walls, deep excavations, would strongly urge you to read and study the case history that comes with the GeoStudio software, especially the PDF document that has been sent with the software, and the data file for all 6 cases are included and can be made available to anybody that is particularly interested in this type of an analysis.